Welcome back. Let us continue our heat exchanger design. As I mentioned towards the end of the previous lecture, a heat transfer coefficient approach is going to be used here because it is much easier mathematically speaking, and for that we are going to express the heat transfer rate as HA times delta T, where this is equation 6.3.2-1, where Q dot is the heat transfer rate, amount of heat transferred per time, H is the heat transfer coefficient, A is the area across which the heat is transferred, and delta T is the temperature difference. Okay. Note that the heat transfer coefficient is not defined for a specific situation until the area and the temperature difference are specified. Okay. You need to say under these conditions of area, because there are various ways by which you can look at areas. There are various temperature differences that you can look at in a particular situation. The heat transfer is going to depend on those aspects. Let us consider the flow in tubes with heat being transferred through the surface. That is a situation here. Okay. You have in a pipe of a double pipe heat exchanger, there is heat in the radial direction, okay, that is coming through the wall of the inner pipe, that is heating up the fluid inside. It is something like this. Okay. This is a tube that I am considering here. This is the heated surface, radially heated surface. Let us say that we consider a length of the tube length, tube of length L. The bulk temperature at this cross section, let us say, is TB1. The bulk temperature at this cross section, let us say, is TB2. Okay. So, TB is the temperature in the fluid bulk, average temperature here, average temperature here, and the wall temperature would be different. Okay. The heat is being transferred here. The layer that is closest to the wall is expected to be at a different temperature if the heat transfer is happening, otherwise the heat transfer will not happen. There has to be a temperature difference. So, let us say that the wall temperature at the cross section 1, okay, it has to be close to this, is TW1, and the wall temperature at cross section 2 is TW2. Okay. So, this is our terminology here. Three conventional definitions of the heat transfer coefficient is what we are going to see next. You could say that the heat transfer, the heat transfer rate is some heat transfer coefficient times the cylindrical area pi d, okay, pi d times L, that is the cylindrical area, times the difference between the wall temperature and the bulk temperature at cross section 1, okay, at this cross section alone, TW1 minus TB1. Okay. So, this H1 is obviously based on initial temperature difference. Okay. So, this heat transfer coefficient that determines that can be used to represent the heat transfer rate is of course based on the initial temperature difference here. Let us call this equation 6.3.2-2. It could also be based on something else. The temperature difference, you take the temperature difference at cross section 1, you take the temperature difference at cross section 2, you take the average of these two. It could also be based on that, right. So, HA times, of course, the area is the same across which the heat transfer is occurring, pi dl, TW1 minus TB1 plus TW2 minus TB2 divided by 2, the average, and HA is based on the arithmetic mean of the temperature difference. There is a temperature difference here, there is a temperature difference here. The temperature difference here is TW1 minus TB1. The temperature difference here is TW2 minus TB2. You take the average, you take the mean. Okay. And this HA is of course going to be different from H1 because it is based on a different way of looking at temperature differences. This is equation 6.3.2-3. Can also be defined in another way. These are three conventional definitions. There are many ways to define it. These three are usually found in the literature and so on. So, you have a Q dot equals the temperature difference now is you take TW1 minus TB1 at cross section 1, you take the difference at cross section 2 and take the logarithmic mean of those. Okay. What does the logarithmic mean? Instead of the arithmetic mean, you have TW1 minus TB1 plus TW2 minus TB2. You divide it by the log of the ratio of these two temperature differences. So, that is the log mean temperature difference, and the heat transfer coefficient becomes H ln. The H ln is the logarithmic, is based on the logarithmic mean of the temperature differences, TW1 minus TB1 ln, which is actually represented as the average, the logarithmic average as written here. Okay. So, these are the three conventional definitions of the heat transfer coefficient. Typically, the heat transfer coefficient based on the logarithmic mean of the temperature difference is preferred because of the operational aspects. It is less dependent on L by D compared to the other things. You have a large length by diameter ratio. Okay. In other words, your length is very large compared to the diameter. In other words, a very thin, maybe a thin radius pipe, long pipe, or a long pipe with a reasonable diameter and so on and so forth. That is the L by D factor. This H ln is not usually dependent on L by D as much as the other two. That is the reason why this is preferred. I think we are going to use this. If the inside wall temperature is unknown, you need to place a thermocouple there, which could be difficult if you already have an existing system and so on and so forth. Or if the fluid properties change appreciably along the pipe, then what do? Okay, the conditions are changing. Your relations are valid only for a differential section. Okay. So, you write your relations for a differential section where you know it is valid, and then you integrate over the length. Okay, simple usual trick. So, if these are the case, if this is the case here, then it becomes difficult to predict the earlier defined heat transfer coefficients, and therefore, we use a differential approach. We take a differential element, a thin element, cylindrical element here of thickness dz, otherwise it's the slab here, the radius is the same as that of the pipe, the only the thickness is much thinner compared to the length of the pipe dz, and therefore, in this case our differential heat that is transferred is H local at the local point times pi d delta z, which is the surface area of this element here, times T w minus T bulk, right, which is the temperature difference here. So, you do not have to worry about 1 and 2 here. This is a differential element, you have this, and you have a reasonably complete description here, and if you integrate, you will get the overall picture. This is equation 6.3.2-5. How are we doing in terms of time? Okay, let me see what we have. Okay, I will probably mention this, and then we will take a break and then come back. Let us consider the heat exchanger now. We are going back to the heat exchanger after giving you some basal aspects of how things are done, general aspects. Let us consider the heat transfer across the heat exchanger inner pipe wall, which is where the relevant heat transfer takes place. So, I have represented the inner pipe wall here. The warm fluid is flowing here and the cold fluid is flowing here. This is the outer pipe, this is the inner pipe. Okay, representation outer pipe, inner pipe. So, inner pipe, of course, there is a center point here and so on. Okay. So, outer pipe is cold, warm fluid is flowing here. So, there is heat transfer taking place from the warm fluid to the cold fluid. Also, I have shown the temperature on this axis with the corresponding distance as shown here. So, the warm fluid is, let us say, at a bulk temperature of Th, And the temperature profile, if you see, there is a region close to the wall, okay, film region again, right, where the temperature drops significantly. It goes from somewhere close to TH to TWH, and there is conduction in across the solid wall here, inner pipe wall. So conduction converts it from TWH to takes it from TWH to TWC. There is another film that is here. Okay, there both are flowing fluids, opposite directions maybe. So TWC and TC is the bulk temperature of the cold fluid. So the overall resistance to heat transfer is the sum of the various resistances which are in series. So you can view the heat transfer having to overcome maybe some resistance here, okay, maybe some resistance at the film, resistance to conduct across this inner pipe wall, resistance to overcome this, and maybe a small resistance here. Okay, we don't have to worry about the resistances in the bulk. Definitely there is this, there is this, there is this. Okay, let us see how we are going to handle these aspects. So the heat transfer problem has been brought down to a conductance across a series of resistances. So we are converting it into an equivalent problem because we can add resistances and so on and so forth. We can use those principles. So the main resistances here are the resistance of due to the warm fluid overall I have taken, resistance of the wall, and the resistance of the cold fluid taken in series, and therefore you could add the resistances. I think let us take a break now. Okay, we have been at it for some time. I think it's best to take a break, then come back and go for a certain length of time. See you in the next class. Welcome back. We are looking at heat exchanger design. We are in our third lecture. We are taking it in small chunks so that we can appreciate it much better. We looked at the heat exchanger as consisting of, or the heat exchanger situation consisting of resistances to heat transfer that are located in series. The resistance in the warm fluid plus the resistance due to the wall and the resistance due to the cold fluid, they are all in series with each other for the transfer of heat from the warm fluid to the cold fluid. So this is the view that we are taking to heat transfer. For the inner, in this case warm fluid, we can write the heat flux as a certain heat transfer rate times the temperature difference of relevance, which is TH, the bulk, minus TWH. Okay, TH is here, TWH is here, that is the temperature difference, and we could write the heat flux as HI in a fluid, TH minus TWH, in a differential section. It is going to change across the length, therefore we are looking at a differential section. HI is the individual heat transfer coefficient for the inner fluid. Equation 6.3.2-6. Then at the wall, of course, there is conduction. We know the Fourier's law. We can directly use that. dq by dAw, okay, heat flux due to conduction is nothing but minus k dt dy at the wall. We have seen this when we began our discussion on heat transport. Okay, dt dy at the wall minus k conductivity is the heat flux at the wall due to conduction, and there it is pure conduction. Equation 6.3.2-7. For the outer fluid, or in this case cold fluid, the flux dq dot dA naught or dAO is HO, the heat transfer coefficient for the outer thing, minus the relevant temperature difference TWC at the wall, okay, wall cold temperature down all the way down to the bulk cold temperature. Equation 6.3.2-8. Now, this is the beauty of using the resistance in series approach. The overall temperature difference delta T, which is Th, the bulk heat hot fluid temperature, minus the bulk cold fluid temperature Tc, Th minus 3c, that is what the overall driving force is nothing but the sum of the individual temperature differences, individual driving forces. Th minus Twh plus Twh minus Twc plus Twc minus Tc. You can see this cancels with this cancels with this, therefore you get back to Th minus Tc. Equation 6.3.2-9. Now, we will have to consider the conduction across cylinders. We need to get an expression for that. We have not done that as yet. Okay, let us see how to get an expression for conduction, so that we can take care of this term appropriately and then bring in these terms for an overall design. So, conduction across cylinders, it is a cylindrical surface. We would like to derive an expression for conductive heat rate across an annular cylinder when the curved walls are maintained at different temperatures. That is the situation here. That is the wall of the inner tube that we are looking at as a annular cylinder here. So, you have something like this, and you have this is the inner radius, this is the lumen. Of course, I have blown it up. Typically speaking, the wall thickness is going to be small and so on, but here to understand, this is the inner diameter, this is the outer diameter. The shell at any distance in the wall is from here to here. Okay, that is what I mean. The shell, we are going to do balances over the shell maybe. So, this is at a distance of r, the outer radius is r0, which is maintained at T0. Okay. The heat transfer is happening in the reverse direction in this case. No, the reverse, it's from the hot fluid to the cold fluid. The inner fluid is hot, it is in this direction, it is from the inside to the outside itself. So, we know from basic Fourier's law, Q dot is minus Ka dt dr. Okay, it is radial this thing. So, minus K 2 pi r L, A is 2 pi r times the L dt dr. Okay. Equation 6.3.2-10. And if you integrate from Ri to Ro, that is what the variation here is, you get 2 pi L k, okay, here Q dot and T naught to Ti dt. You are getting r's to one side and so on and so forth. Q dot equals minus 2 pi r L dt dr. We have taken r to one side and the temperature on the other side and so on and so forth. You know this manipulation, and then we are integrating to get Q dot equals k times 2 pi L Ti minus T naught divided by ln Ro divided by Ra. Okay. So, this is what you get by solving this equation here, integrating this equation here between the limits of Ri here and Ro here, and going from T naught to Ti. The temperature there is a minus here, therefore, that gets taken care of. Q dot is k into 2 pi L Ti minus T naught ln of R naught by Ri is what you get from that expression. This is equation 6.3.2-11, or you could combine some terms and call the combination as Al dash or Al hash Ti minus T naught divided by Ri minus R naught minus Ri. And what is this Al hash? It is logarithmic mean area, which is defined as 2 pi L, which is fine, 2 pi into L, it is fine. The radius part of it is defined as Ro minus Ri divided by ln of Ro minus Ri. So, ln of Ro minus Ri is here, and Ro minus I needed a Ro minus Ri on top to convert this here, therefore, I need to introduce Rho minus Ri in the denominator here, which has been done, and this has been combined into a AL hat. In other words, 2 pi L into a log mean radius. Okay, that is log mean radius here you can see is Rho minus Ri divided by ln of Rho divided by Ri. This is equation 6.3.2-13. RL hash is the logarithmic mean radius as defined, and if we use these at the heat exchanger wall, that is where the conduction is happening, we can write dq by dA LW hash, logarithmic mean area at the wall, equals k times TWH minus TWC divided by XW. Okay. So, you substitute all this back, you will get this into, you differentiate this, you have an expression for q dot written in terms of logarithmic mean radius, and then you substitute it back here. Why are we doing that after integration? You will see very quickly. The other two forms are still in the differential forms. Okay. So, you have this equation 6.3.2-15. So, if you substitute this back into the overall expression, Th minus Tc is one temperature difference on the inside plus the temperature difference at the wall plus the temperature difference at the outside, right. That written in terms of the rate and the heat transfer coefficient is this. So, dq dot by dAi hi plus dq dot divided by dAl hash xw by k plus dq dot divided by so dq dot dA naught ho is Th minus Tc. Equation 6.3.2-16. These are derivatives here, dq dot dAi hi and so on. dq dot dAl xw by k, dq dot dA naught 1 by h naught. Okay. Therefore, dq dot by dAo, which is this, can be written in terms of the other quantities from this equation, Th minus Tc. This is what we are looking for. Therefore, you add terms to the other side, and or you take that one common out and then bring the whole thing down into the denominator here. So, we have taken dq dot dAo out. So, you have a dAo dAi times 1 by hi remaining here. You have xw by k dAo dAl hash remaining here plus 1 by h naught remaining here, and that goes to the denominator on the other side to give you this. Equation 6.3.2-17. We know that the ratio of the areas is nothing but the ratio of the diameters, because 2 pi L is the same, right. Pi d into L or 2 pi r into L, therefore, the L is the same, pi is a constant, and therefore, the ratio of the areas of interest, the curved surface areas, is the ratio of the diameters, and dAo dAl can be written as dO by dL. dAo dAl hash can be written as dO by dL hash, the logarithmic mean diameter. Therefore, you could replace these as dq dot by dAo equals dq dot dAo equals Th minus Tc. Instead of areas, you have the diameters, 1 by hi remains, plus xw by k d naught by dL hash plus 1 by ho. This is equation 6.3.2-18. Now, we know that flux in general is a driving force by resistance. Okay, you can express flux as a driving force by resistance. 1 by resistance is nothing but the conductance, and therefore, you take 1 by resistance as conductance. So, conductance times the driving force is flux. Therefore, the conductance is nothing but this. In this case, the flux is this, the conductance is 1 by of this times the driving force is Th minus Tc. Therefore, you could write the conductance UO as 1 by d naught by di plus times 1 by hi plus d naught by dl hash xw by k plus 1 by h naught ho. Equation 6.3.2-19. U0 is called, or UO is called, the overall heat transfer coefficient based on the outer area of the inner pipe. Okay. So, this is where the outer area of the inner pipe, inner area of the inner pipe. Why? Because you have a pipe. This is a physical pipe. A physical pipe has a certain thickness. So, there is an inner diameter and there is an outer diameter for the inner pipe alone. So, you can have an area based on the inner diameter of the inner pipe and an area based on the outer diameter of the inner pipe. Okay. So, this overall heat transfer coefficient UO is based on the outer area of the inner pipe, because we have normalized with respect to the outer area. Similarly, it can be based on the inner area of the inner pipe, as if you pull out the corresponding different areas, you could either pull out we pulled out this area here. If you recall, we had written it in terms of, we had pulled out dq dot dAO out. Instead, you could pull out dq dot dAi. Then the other things need to be written in terms of these aspects. That is what is meant by the other approach there. So, if you do that, you could do that also. It is just a different basis. The overall heat transfer coefficient based on the inner area of the inner pipe would be this 1 by hi d naught by dl hash xw by k plus di by do 1 by ho. Okay. This of course I have not shown, but you will have to go back, pull that other term out and write it in terms of and rederive that a few steps you would get here. Let us call this equation 6.3.2-20. Now, we have good enough background to address the problem. From the schedule number that is given, the nominal diameter given, you can find di and do from the relevant tables, and using that the following can be calculated: di minus do divided by ln of do by di, the logarithmic mean diameter. This has to be do minus di, please, minus is missing here, and the heat transfer coefficient based on the outer area of the inner pipe is whatever we have already seen, 1 by d naught by di, 1 by hi plus d naught by dl hash xw by k plus 1 by h naught. Also, since q dot is u naught a delta t, the q naught is nothing but the energy removed, which can be calculated if area is known. Now, everything else is fine. You know d naught, you know di, you know xw, the wall thickness, you know the conductivity. How do you find, and dl hash can be calculated. If you know hi and ho, you solve the problem. Okay. Hi and ho are the individual heat transfer coefficients. How do you find them? Correlations are available in the literature to find out hi and h naught under specific different conditions. Of course, they depend on the condition, and a different correlation is valid for each condition. Okay, this is what makes it a little difficult to use. Whatever correlation we use needs to be applied to that exact condition, and we have no confidence whether that correlation is going to work for another condition. The correlations are usually written in terms of non-dimensional variables, of course, to better generalize their applicability. This is to be expected. Let me give you examples of a few correlations. For highly turbulent flow, okay, first the flow is highly turbulent, Reynolds number is very high, and for the L by D ratio, the length by the diameter ratio, that has to be greater than 10 under these conditions, and if the bulk Reynolds number is greater than 20,000, then okay, if these conditions are met, if the bulk Reynolds number is greater than 20,000, if L by D is greater than 10, then this correlation works. This correlation has been found through number of experiments, and then in some insights and so on and so forth to come up with this in terms of non-dimensional quantities. Epsilon d by k equals 0.026 rho v d by mu b. Mu b is the bulk viscosity raised to the power of 0.8, Reynolds number raised to the power of 0.8. Cp hat mu by k, Prandtl number raised to the power of 1 by 3, mu b by mu w, viscosity of the bulk divided by the viscosity of the wall, temperature affects viscosity, therefore you need that difference raised to the power of 0.14. Okay, this correlation works for this condition. Equation 6.3.2-22. This epsilon d by k is called the Nusselt number, which one comes across very frequently when you have heat transfer situations with flow. Thus, Nusselt number, the logarithmic mean Nusselt number is epsilon d by k, which is based on the logarithmic heat transfer coefficient epsilon. Also, let us recognize that this is the Reynolds number power of 0.8 as I had already mentioned. This is the Prandtl number as I had already mentioned. Also, bulk viscosity at the wall temperature. And for laminar flow, this we said for turbulent flow, the bulk Reynolds number greater than 20,000. For laminar flow, a different correlation works. Epsilon d by k equals, instead of 0.026, you have 1.86. Reynolds number, the product of Reynolds number, Prandtl number and d by L raised to the power of 1 by 3. Everything raised to the power of 1 by 3, the product raised to the power of 1 by 3. This is bulk Reynolds number, this is bulk Prandtl number, d by L raised to the power of 1 by 3 and mu b by mu w raised to the power of 0.14. This is for laminar flow. When the flow changes, your correlation changes. Equation 6.3.2-23. So, you use different correlations that have been developed for different conditions in the literature. You have correlations that are very different for free convection, when temperature differences in the fluid set up density differences, and therefore, the flow occurs. Lower density fluid rises, the higher density fluid drops, and therefore, a flow occurs. Okay, that is free convection. There could be phase changes that occur in these cases. When a phase change occurs, a totally different correlation is valid, even in the earlier case. If you have a condensing liquid, then a different correlation. If you have a cooling liquid, then a totally different correlation, and so on and so forth. So, you need to know the conditions, you need to know the operating conditions, you need to know the physical conditions of the fluids, and then you need to choose a corresponding correlation. Hopefully, that correlation is already available. If not, you will have to develop the correlation, which is not an easy thing to do. A chart similar to the friction factor chart can be used when the Reynolds number is greater than 10,000. And in that chart that is available in handbooks, you have the product of the Prandtl number and this is the Nusselt number and the Prandtl number raised to the power of 2 by 3. This product happens to be related to the friction factor by 2. Okay. So, this is called the JH factor, which is approximately equal to the friction factor by 2. So, this correlation can be used, which simplifies various calculations. This is called the Chilton-Colburn analogy, and the properties are calculated at the mean temperature of the bulk and the wall taken. Okay, Tb plus Tw divided by 2, the average of the two. And there are other useful formulations. You can read the textbook, your textbook for some formulations. You can read other books on heat transfer, mass transfer for many other formulations. The heat transfer, mass transfer books are filled with correlations of different kinds for different situations. I think that's all I have now for you. With this, we have looked at the essence of heat transfer exchanger design. It's a operating piece of equipment available, that is right there. The way to design it, we have seen the intricacies of designing that, or the principles that go into design that we have seen. And of course, if something is going wrong, you can go back and start looking at it from these points of view to get a handle on how to operate it better. Okay, I think we have completed the course with this lecture. In the next lecture, let us start with a review. I think we'll do the review over a few lectures. That will be useful for you. The review will help you see things in perspective. You've done each one with a focus on that aspect alone. There are beautiful insights to be drawn when you look at them together. We are going to draw some insights, as well as we are going to review the entire course in the next few lectures. See you then. Bye.